So there are technically two different calculations for standard deviation. We saw them in today's notes when you get that calculator output. And I just want to unpack those two calculations a little bit. And the key for us to start our conversation is to realize that we have a population and we have a sample. The population is the true value for the entire group. And the sample is true, but we're only looking at a small number of them. So an example of this, you might want to talk about all EHS high school students, and you've got 800 of them. And you could ask all 800 of them some detail in order to get the true population standard deviation. Or you could just poll our class, and that smaller group of our class would be a sample. Another way to think about it is you might poll all 800 EHS students, but you might want to speak about all high school students in the US. Now, those 800 EHS students are your sample, and the population you want to speak about is the entire population. The idea here is we are in a quest for our sample to be as close to the population as possible. That's our end game. We want to look at a sample because it's easier to collect a small number of data points, but we want enough accuracy to be able to say, we think this is true for everyone. And so as an example of that, dice rolls. If I were to roll a dice 6 times, we would expect 1, 2, 3, 4, 5, 6, because we would expect it to be even amongst all the numbers. But we know for reality, that's not going to be the case. I got a 1, I got a 6, I got a 6 again, I got a 2, I got a 1, I got a 6, and a 6 again. So I ended up getting 4 6s at, well, I just did that 7 times. Whoopsie. There's 6, okay? 6 3 times though. And so here's the deal. If we were to take the average or find the standard deviation of this, which doesn't quite make sense because it's a dice roll, the idea is we are going to get different values than reality. And that's what our two calculations try to correct for. They try to say, hey, when you take a sample, you're going to get something different than reality. Okay? So we have our population standard deviation that uses sigma. We've got our sample standard deviation, which uses S of x. Here, there are two equations. You'll notice they're almost exactly the same. I'm not going to go under the full unpacking because that's in part 2. Here's what I want you to see. This letter right here, that is just the letter mu. It's a Greek letter, and it represents the population mean. So while this was the mean for our data set, add them all up, divide by how many, this is the if you knew what it is for the entire group you want to speak about. So that's the same. So the only real detail that changes is the n becomes this n minus 1, which is kind of an interesting idea. And why does that happen? I'll be honest, it's kind of a challenging idea to wrap your head around, but here's the basis of it. Since mu, our population mean, and our sample mean are not the same, right? Because if I pull a few values, that average is going to change. We can see that up above. What would have been an average of 3.5 is going to be a lot closer to 6 in this example. So because the means are not the same, it turns out that when you go through the process of trying to calculate everything, the data will be closer to your sample mean than the population mean. As a result, this S of x is going to be bigger. And so in order to make this smaller, is going to be smaller. So in order to fix that, we need to divide by a smaller number. Hence, n minus 1. It needs to be smaller in the denominator. In order, or why we pick n minus 1, you don't need much of an adjustment, and it fits in a situation. If your sample only has one data point, it really doesn't make sense to talk about variability, because how do you have the variability of one thing? So if you imagine plugging 1 into this equation, that becomes a 0. We can't divide by 0. The formula fails. So mathematically, it just fits nicely to use that as a logical rule.